We're going to continue talking about momentum and hydrostatic balance. So we talked about this, we hinted at this last time, the weight of the stuff above you is the hydrostatic pressure. So we're going to talk a little bit more about how that comes from the momentum equation. And so that will be, that's going to be our first example of a momentum balance, but we're actually going to study seven different momentum balances that are different terms in the equation, taking a dominant balance one at a time. So this is what the first example, and this one is kind of easy to wrap your head around. Then we're going to have the other ones are going to involve the rotation of the planet. And so we've got to do a crazy rotating momentum discussion, which is a bit like mind bending. So it will take more time to do those other ones. This one I hope is going to be fairly straightforward. So in addition, I wanted to talk about some topics about the papers, give you all some opportunity to discuss a little bit like with your neighbors, what you're working on, and like decompress possibly. We'll do that again next time as well. So like hopefully you're, maybe that person might be your peer reviewer or something. You have an opportunity to kind of think that through, or even what you're looking at towards that as we start to close down on the first projects. I'm happy to keep doing that if that seems useful as we go into later papers. It's a different, this is such a big class. We have lots and lots of people. So I feel bad that people don't get to speak very often. I would like to rectify that. So that's also a model that I thought would be helpful for that. That sound good? Because I think it's at least, well, I'm sure you can tell this already. I think by speaking out loud. And so like, I find it very helpful in clarifying particularly the story I want to tell, just to try to tell somebody else what the story is. And then I learn from that, and then that becomes the paper. And so that's a useful process for everybody to do. So I want to start making that part of the process as we go along. Cool. All right. So as I said, next time we're going to talk about the momentum equation for a rotating planet or a rotating tank. And I know rotating tank sounds like totally bizarre, but it turns out there's a close analogy between a rotating tank of water, like on a record table, versus a rotating planet. And we'll see how those connect next time. And it will help us like think about it. And we can look at lab experiments and start to get a handle on why rotating fluids are so weird. And that will be something that'll help us as we go back to try and interpret what's going on the planet. Okay, so we're going to talk a little bit about abstracts and introductions and the required sections on papers before we have a little discussion about where your papers are going. Then we're going to come to this hydrostatic balance, which is fairly straightforward, but we want to make sure that it's our first example of something that's going to become not straightforward soon. Okay. This isn't the way that I learned to write an abstract, but it's so admirably precise that it's kind of useful to know. This is what Nature says when they ask you. So every Nature paper has a summary paragraph, which is like an abstract. It's a little bit more than that. In that some of these, I think, lead into what I would normally put in the introduction. But like if you go to Nature, there's a big paragraph at the top that's like in bold font. And that, by the end of that, you know whether or not you want to read the rest of the paper. And so this is how they lay it out, or they ask their authors to lay it out. And it does serve the purposes of the abstract. So at the simplest level, like how do you decide whether you're going to read a paper or not? Like you read the title, you check out who the authors are. And then if you're like still interested, then you go and you find the abstract. And the abstract it's a lot of journals, the abstract is the only thing you can get for free. Then if you try and get the rest of the paper, you have to pay for it. So the abstract is really kind of an important object because the title is too short to tell you what you really have done, even though that is actually the goal of the title, is it should be catchy and descriptive of the science you carried out. And then the abstract is a longer form. So these little colors are telling you whatever. So 1 or 2 sentences providing a basic introduction to the field. So during cell division, mitotic spindles are assembled by microtube-based motor proteins. I mean, that's not really broad language, but this is for a science paper, so you don't have to explain that to a kindergartner. you are talking scientist to scientist, like that's the level of abstract. Then 2 or 3 sentences, a more detailed background. This is the part that I would actually cut from ours. But if you want to follow this recipe exactly, that's fine. Then 1 sentence clearly stating the general problem being addressed by this particular study. This is where I would say is you definitely should have that. And maybe you cut those and put those in the introduction and start here at yellow. But, you know, that's up to you to decide. Then 1 sentence summarizing the main results. So here we find bang. That should echo, these 2 should echo the title. Because the title should say, it is such and such that Bing, like that's the title. And it tells you kind of the problem you're working on and whatever. This is a 2-sentence version of your title. So it's expanding out. Then there's the main result contrasted versus the traditional understanding. So that's a little bit about like, is this a surprising result? Is this confirming earlier work? That's a really helpful thing to have in your abstract. 1 or 2 sentences to put the results in a more general context, like this means, and then 2 or 3 sentences to provide a broader perspective, readily comprehensive. This part, I also could think this might be the conclusion of your paper rather than here. But these in the middle are really what an abstract is about. And what I would say for sure is you should have a number in your abstract. Like we're doing a quantitative field, some number out of all of the things you have thought about rises to the level of being in the abstract. So if you're measuring the temperature at 2 locations, you can say the mean temperature is this and the mean and the standard deviation is this. Or in these 2 locations, they were seen to differ by 0.3 standard deviations, something like that. Like that kind of a key summary statistic is always helpful. And you'll find as we go on that some of the things you're doing, actually the number is the most important thing. Like the transport of the Gulf Stream is 30 spheroids, like in this particular location, something like that, very often rises. So the main results, probably not a number, but there's some numbers in here, maybe clarifying what the main result, how it, you know, maybe your main results is 1 spheroid different from another main result. That would be here in the discussion, you know, and then does that make sense? Makes sense to everybody? Everybody has everybody written an abstract before? Maybe some people are looking sort of, all right. This is a hard thing to do. It's going to take iterations to get good at it. The other thing that we have going on is we're using the geophysical research letters format, which means that this abstract has to be less than 150 words. This one is probably more than 150 words. So you're talking that much is about 150 words. So there are a lot of challenges. This is part of what this is like what makes it fun. So what's the difference between abstract and introduction? They're both at the top of the paper. The introduction is the next thing you might look at after the abstract. The introduction doesn't usually have any results in it. The introduction motivates why you did the work. So those first sentences and the last sentences are kind of, the first sentences are like an introductory idea, the last sentences are like a concluding idea. And almost every citation you have in your bibliography is going to appear in the introduction. So like, even if it's like a method that you're borrowing, in the introduction, you might say, we're going to adapt the method of so-and-so in order to examine such and such. That first citation appears in the introduction. And then when you go to the method section, you said the method of so-and-so can be more clearly explained in this context as being the equations. Does that make sense? And the introduction normally doesn't have, it can have equations in it, it normally doesn't. Depends on whether the equation is like a central idea that you're exploring or not. And some of our papers fall in that category. And the key idea is that it introduces for the uninitiated. It's still talking to other scientists. So it's not the uninitiated to science, but it's uninitiated to your particular topic. Maps are a really good thing to put in the introduction. Just like, where in the world are we? Put a map in it. Label some of the things you're going to talk about. That will help pull together the ideas. Put the current, the approximate location of the current you're going to think about. Put a sea surface temperature map that's just a vague one. That's not specific to the later detailed analysis, but just kind of sets the scene for everything you're going to talk about. This is like the scene setting phrase, whereas the abstract is really includes the method and includes the main results. That's it. So it's a tighter piece. This is 150 words. This is any length you want. Okay. Questions? And you're going to see that, like, as you've seen a few of these, both of the papers you're looking at, find material for your paper, but also as you peer review other people's papers, frequently you're going to see something that's in the abstract that shouldn't be there, or something in the introduction that shouldn't be there, or something that's missing. And then that's a good recommendation to make as a peer reviewer. Like, I thought this was your most important result, but I didn't see it in the abstract. That's a great critique to make for someone's paper. Okay. All right, so the last thing on this paper is before we break to have a conversation about your status is, what do I think is going to be in your paper? So there are requirements that are specific to this class, but also specific to GRL to something. There will be a title. There will be an author, which will be you. There will be a date, which will be the date that you submitted it. There will be an abstract, which will be less than 150 words. Okay, so then there could be, but there almost always is an introduction. The introduction does those other purposes. Sometimes it's called background. Doesn't really matter. Could be called something else too if you thought there was another title that was more descriptive of exactly what you're going to do there. But introduction is fine. Then theory and methods. I added this one in red because a lot of people were not telling me exactly what you did in comparison to the class work. The theory and methods is where you say, this equation shows the hydrostatic balance. We're examining the hydrostatic balance in this paper by, we found a pressure like this and we found gravity like this. So this is the section where you take what we learned in class or what's in the book or what's in a paper you read and you just drop it in there and say, this is the methodology I'm following. Sometimes it's called theory, sometimes it's called methods, sometimes it's called theory and methods. It doesn't really matter, but there needs to be that section there where you're actually linking to the kinds of ideas we're using in the class. So for those of you who are doing a budget, you might say a budget is constructed like this, where I'm looking at a salinity budget, the standard equation for a salt budget into a control volume is the following integral. That's what we're going to examine in this paper. Or if you're doing statistics, you might introduce this mean and standard deviation, the bootstrap or something like that in the theory and methods. You can add some other references that are going in there, but some of them, they probably appeared first in the introduction. Any questions about that? Okay, results and discussion. Results is what you're doing the whole thing for. There are some results you found. Good. Sometimes it's results is this own section and the discussion is a separate section. The discussion is where you do that part where you contrast the other papers' results, or maybe you talk about something that you couldn't do that you wanted to do. Like, if only we had more observations, we could do this. So the results are giving a deeper the discussion is giving a deeper reading into your results than just presenting the results. But if you don't have anything to discuss and you're just reporting, you don't need a discussion. That's why this is in green rather than red. You can drop the discussion and just put the results in. If your results are figures, that's good, but it's not enough. Every figure should have at least one sentence referencing it and saying what's in the figure. And every figure should have a caption. It just says, like, what are the symbols in the figure talking about? It's great if you don't need a detailed caption and you can interpret the figure because it's got good labels on the axes and like it's clear in the context what it is. But sometimes like you'll just have like a line with like numbers and numbers. And then you're like, well, what is that thing? Like, what are you trying to say with that? So you need a caption that says what the line shows. You need labels on the axes, and then you need a sentence that says, why is that the thing you chose to plot? Because it's talking about this result that we're trying to build towards. Okay. Then there's a conclusion and or summary. It could just be a summary of your results again. Shorter version bullet points. It could be a conclusion, which is kind of like, we found this. Could be a conclusion and summary. It could be, sometimes some of the discussion pieces end up in the conclusion, like our results showed no significant effects, but if we had other data, we might have gotten something different. That's the kind of thing you would take away messages in the conclusion. Often future work directions kind of things ends up in the conclusion. Then acknowledgements are another required section. And the most important acknowledgement for our class is if you got code or talked to a student and somebody else, or you both developed the same analysis toolkit, but you would apply it in different places, you need to acknowledge your partners in crime here, where this is like, that's the way that you're avoiding plagiarism, is you're talking about the collaborative work that you've done that goes into your paper. If you really work very tightly with somebody else, you might choose to make them a co-author, where you're the lead author and they're, but that 2-author paper does not count for 2 submissions to this project. You need to flip the author order and write another version of the paper with the other author being the lead. So you have to write a first author paper for every assignment in here. You don't get to collaborate and eliminate a paper. Does that make sense? Even though you can collaborate very heavily, maybe even sharing co-author, but certainly sharing code, because you couldn't figure out how to do something, but somebody else figured it out. Great, take their code and use it, and then you just acknowledge that you received that piece of code that helped you make figure 3 from so and so, and that's exactly what you would do in the real world. We do have co-authorships. Almost all papers in oceanography are multi-author now, like fewer than 10% are single author. So we're always working together. And then lots of other stuff goes in the acknowledgements. One thing that you'll find in all the papers is every grant that funded the work gets mentioned in the acknowledgements. So why is it important to acknowledge the grants you got from a scientific perspective or other perspectives too? They paid for it, so they should get credit. But what else from the science side?
Know if there's any like contradicting interest.
Conflict of interest. So like think about a pharmaceutical company. You're like, Ozempic is the best drug there's ever been, sponsored by the makers of Ozempic. You're like, oh, I actually don't think I believe that study is quite the same way as if it was sponsored by somebody else. So even though we're trying to maintain distance and objectivity, it's still really important that you mention your sponsors. That's one of the most important ways that you insist objectivity. In fact, is that you say, even though I was paid by them, not all of the results go the way they wanted it to. Like, that's kind of a way to think about it. All right. Every figure deserves 1 sentence. Okay, publication units. This is a bit weird. There is no minimum length for these papers. Realize, however, that you're being judged on the completeness of your paper. So if you're missing something, one of these required sections, then you have missed it. You're going to lose points for that. But it's not like this is a 5-page paper, and if it's 4 pages, you're too short. It's like if you do what you need to do in 4 pages, awesome. That's great. You know, like no problem. It'll probably get a little longer in response to peer reviews. That's fine. But on the long side, and many people produce a lot of things, there is a limit. So there are 12 publication units allowed. A publication unit is 500 words, which is approximately a page of text, or a figure, or a table. So if you're thinking now, I've got 10 awesome figures that I'm going to put in my paper, that means you've got 2 pages of text to do all of this stuff left over, which is pretty tricky. So you probably can't use 10 figures. You need to decide how to sub-select from those figures. On the other hand, if you blow it all on words, you got 6,000 words, which is an awful lot. That's probably not helping your cause very much either. You're trying to balance between the number of figures and the amount of text. And so that's what you're trying to do. This little formula is kind of like weirdly bean counting, but it does kind of actually keep things right to about the size you want them to be. Some of them really are more natural with fewer figures and more writing, and some of them are more natural with more figures and less writing. It's up to you to figure out what works best for the project you're on. Does that make sense? So this is the number of words divided by 500 plus the number of figures plus the number of pages. Now, is a figure a sub-panel or is a figure a collection? If you put like 8 sub-figures and they don't have anything to do with each other, that is not one figure. That just means they're too little to read. So a figure might have more than one panel, but it's be related ideas. So maybe you're showing the sea surface temperature in 4 locations, that's still just one figure. But if you're showing like sea surface temperature and chlorophyll and then and analysis of the momentum budget and then all, like, that's not one, those are each separate figures. So you should make them big so they're readable. Don't try and squeeze them into all on one page just to save on this formula. That's not, we will see through that. Okay? Yeah.
Can we have supporting material?
You can, but it counts towards these publication units.
I thought it's.
It is included. The appendices are included.
Oh.
So this is different from Nature and other journals where you could dump a whole bunch of stuff in the supporting material. And actually, I think it's not, it's important for this class because I don't want you to feel like you can, I want you to choose carefully about what you're choosing to present. And I want you to be graded and peer reviewed on everything you submit. What happens with those supplementary information is people will put like a 50-page supplementary information on a 3-page paper. And then everybody is actually digging around the supplementary information, but it's not very carefully checked in the way that the 3 pages are. We're trying to actually look at everything you send and review you on everything you send. So it may make sense to put an appendix because something is like a complicated math calculation and it would just be distracting in the middle of the paper. So you might put it in the table, in the appendix to make the paper flow better, but it's not a place you can hide extra figures. Okay, does that make sense to everybody? And this is for your own benefit because you should stop when you have run out of publication units. Like you don't need to, more is not better. And also you need to learn how to stop. We talked about this before. It's okay to say, one could examine this other thing. It is not within the scope of this paper. That just knocked off an entire section with 20 figures in it. That's not what we're trying to do here. We're not trying to be exhaustive. We're trying to tell a logical story that allows you to think much deeper about the concepts we're presenting in class. Okay. All right. So discuss with a neighbor which paper topic or the challenges you're having now. What was easy to do? So 5 minutes or so. I'm gonna go get my water bottle from upstairs. Pick a neighbor and discuss.
What are you doing?
I'm an engineer, so I don't really know about Okay, how much? The idea of global warming, so it's like how Yes, right. Yes. When the ice freezes, there's like more stuff. Right, and it can like vary over time. Actually, do you want to exchange contact information? I feel like.
Yeah, and then.
So it sounds like things are quieting down a little bit. Does anybody want to reveal something that was interesting in your conversation that would be useful for other people to think about? Share back to everybody. El Nino and La Nina cycles, yeah, we're gonna come to El Nino and La Nina in the like at the end of class and talk about it with a lot of sophistication. But those kind of ideas are cool. What came up in your paper?
So I think both lawyers have like the same problem when you're looking at FSC change and synthetic temperature, and you're trying to kind of remove the signal or maybe
Isolate it, yeah.
isolate it, and it becomes, okay, if you remove the signal, then what are you, maybe you're left with only so much, so few data points to look at. So it's just something, I don't think.
Yeah, so a lot of the statistical papers involve like categories that you're comparing, like that's a really nice way to think about it. But like the choice of those categories is important in a lot of ways. Like if you take too much out, what's left over is not very rich in terms of what it's describing anymore. And you put too much in, it's probably smearing together a bunch of things. So that should be attention. That's constantly attention, right? And so part of the reason why we're working with all these equations and things is it's going to help us like laser focus on a particular idea. And then you can pull just those pieces of the story out. Then we move to the next idea. You're going to do that. And so we're going to talk about complementary balances in the momentum equation. And you add them all up together, and you end up with almost the total momentum equation, which is what Echo is solving for. So that's going to be like the big concept of where we're going. But we got to first think about each of the separate balances individually and kind of get a handle on what it means. Because putting them all together into the big stories toward the end is going to be like a lot of layers of extra stuff that we need to put on top. Okay, so that's where we're going for the next few weeks, is trying to build separate dominant balances, is what they're called, and then think about how they fit together. Anything else for your favorite discussion? Okay, so like I said, we're gonna have another one on Thursday, and so give it another chance, so you can talk to different. You don't have to sit in the next necessary. We can put a digital chair and something. Yeah. But that's, yeah, but so. The peer review process, you're gonna get to see two papers from two other people. So part of the cool thing is even though you're focusing really on one particular topic for each of these papers, you're gonna learn about other regions of the world or other, examples of doing the same thing, because other people are gonna choose different things. And if you're choosing exactly the same thing, I will gently nudge you at the plan stage to not do exactly the same thing, to make sure that even if you end up reviewing each other's paper, you're not doing the same thing, you're doing something slightly different. So that they can be complementary rather than like overlap. Cool? Okay. So here's our big set of equations, which we have not tried to derive, but we just say these are what they are. And we talked a lot about the potential temperature in the last couple times. So where does potential temperature appear here? Or thermodynamics? The definition of this guy, yeah. So this one, so there's like maybe a temperature there. Yeah. And the temperature here is talking about internal energy and entropy, which is part of this thermodynamics. And then here are two thermodynamic equations. So this one is an internal energy equation, and there's a compressibility factor. This is an entropy equation. Entropy actually, at least in the ideal gases, is like a relabeling of the potential temperature. The potential temperature is really just the entropy. And that's also true, not quite as clearly in ocean flows. So the potential temperature is like, we said it's an adiabatic expansion. So adiabatic means that the energy is being conserved, but it's also not mixing or doing anything else. So it's preserving its entropy. Okay, so that's where potential temperature appears. That's an equation for it. This is a material derivative. So what does that mean? Follows around with the motion of the fluid. So it's a time derivative, but it's a time derivative not at a point. It's a time derivative following along with the fluid. Now we talked about budgets where we can convert between following the fluid and like a fixed volume and having stuff flowing in and out. That's one of the tools we have to interpret what this means. We've talked about that in detail. This is the conservation of mass budget. This is the conservation of salts. This guy is the momentum equation. And this one is kind of stripped down, and then it just shows the pressure gradient force and the material derivative of velocity. Normally there's some other forces. Gravity is a primary one that we're going to talk about today. It just gets added on. So what does it mean that the material derivative of the velocity balances the forces? This is an acceleration. So it's following a hunk of water. It could accelerate. And when it does, the acceleration is a vector quantity, right? So this is a time rate of change of a vector. So the answer would be a vector. And so that's just the acceleration. Here's something that's kind of like mass over here, density. We brought it over there. It would be mass times acceleration equals forces. So this is just Newton's second law, F equals ma, written in the fluidy form. So it's all hidden and kind of complicated, but that's what this is about. It's the external forces applied to the fluid results in acceleration. Pressure gradient is weird because the pressure gradient is sort of an external force, but it's also part of the fluid. So the pressure is there because of the properties of the fluid, particularly the equation of state. But we don't normally include it with The acceleration, it's not an acceleration exactly. It's a separate thing about the way that liquids behave. And the main thing that we've thought about so far is that they resist compression. So if you push on them, the pressure pushes back out at you. So this pressure gradient and finding out where it comes from and the different circumstances is going to be a lot of our challenge as we think about momentum balances. The hydrostatic pressure is indeed a way of thinking about where pressure comes from in the case where it is hydrostatic. So what does hydro, it's static mean?
Still water.
Still water. So how is this equation different if the water is still? There's no velocity, so this side's zero. So we got a pressure gradient and maybe some external forces. That's going to be our hydrostatic. Okay, so here we go. I've written it much bigger and I've added gravity. And this is not obviously bold, but that's a vector gravity. So we're not sure what direction it's pointing at. So this is the acceleration. This is the pressure gradient. This is the gravity. Good. Does it have to be totally motionless to consider a hydrostatic balance? So if I could consider what happens if I set this to zero. What if it's moving but just not too much?
Sounds good.
Sounds good. So how much is not too much? It can be constant motion, and then I could change my frame of reference. That's one very sophisticated one. Or the fact that this is DDT is something, if it was constant in time, this would also be zero. Good. But how about this term versus this term versus this term? We don't know where this one comes from. It seems to magically do whatever it needs to do. That's one way to think of the pressure, is it figures out what else is going on in the other terms in the equation and manages to make the balance work. What about acceleration versus gravity?
The size of them is very different.
Yeah, so what's an example of something that's accelerating at the same rate as gravity? Exactly. Something free fall, right? So that's pretty fast. In the ocean, things, aside from the waves at the surface, not many things are moving in the vertical that fast, or even in the horizontal that fast. So this term is probably small in comparison to that term most of the time, which means that even though the hydrostatic balance formally means let's set this equal to zero and let the pressure match this external force, the pressure might be pretty close to that hydrostatic pressure, even if this is non-zero. Okay, so that's one of the pieces we're going to think about. All right, we can play our games. We could do, this is what our equations mean, even though they're differential equations. We can integrate them. And the main one that when we think about the momentum equation, we're thinking about rho u coming in and rho u coming out. Rho times u is the density times the velocity. That's really the momentum per unit volume. So this is momentum coming in. This is momentum going out. So momentum in the box is what compared to the coming in and going out? How does the momentum in the box stay fixed? All the fluid inside the box, does it think about its momentum? Is it fixed or could it change? It could change because we might have more momentum. Who knows what more means in a vector quantity yet? More momentum coming in than going out, or we could have more going out than coming in. And so the momentum in the box is just like the salt in the box or the water in the box. When we talked about the salt salinity budget and the estuary, can change depending on whether there's inflows or outflows that are in balance or not. This one has u, so often we use u for the x direction, y V for the Y direction of velocity and W for the Z direction of velocity. But I also could have made this U a vector and it could have been A into 3. So this is a bit complicated because the water that's coming in might actually also have some V momentum to it. It might be coming in at an angle. In which case, the inflow in U might be doing one thing, and the inflow in V might be doing something different, and the inflow in Z, W might be doing something different. So we really have 3 different budgets in the momentum budget, one for each component of the momentum equation. With the vector, and each of those 3 directions, how about the forces? Does every force affect all 3 directions? They're shaking their heads. What's an example of something that doesn't? Gravity goes down, right? So the gravity has a one particular direction. Actually, every force, when you sum them up, will have a net direction to it, at least transiently. And so we're going to be thinking of a source of complicated forces, complicated inflows and outflows, rate of change of stuff inside the box. All of those are allowed in our momentum equation. Okay, so here's our mass conservation. Notice how it has a rate of change, which we've been thinking of as the rate of change inside the box, the partial derivative, and then the divergence of that flow coming in and out. So it's a U times the thing that's being conserved. This is the same. It's a U times the thing that's being conserved. Actually, we have to be careful here because this derivative is on the I, this is on the J, and that's on the J. So the thing that's being conserved here is rho times UJ, and it's being brought into and out of the box by another velocity. So this is a super weird thing. This is a second-rank tensor. It's a vector product of 2 vectors, or it's an outer product of 2 vectors. So there are actually 9 different one of these. There's the U velocity bringing in the U velocity, but there's also the U velocity bringing the V velocity, and the U velocity bringing the W velocity, and the V velocity bringing the U velocity, and the V velocity bringing the V velocity, and the V velocity bringing the W velocity, and the W, and so on. This is a very rich set of things. This is conservation like we talked about, just one direction at a time. Momentum in this direction in the box, momentum in this direction in the box, momentum in this direction in the box. So this guy is. The pressure gradient has only one on it, and it's the same one as this. So if I push that way, by having a high pressure here and a low pressure there, I'm going to tend to accelerate the stuff in the box in that direction I'm pushing. If I push the other direction, I tend to accelerate in that direction. Push in this direction, I tend to accelerate. If the pressure is the same on both sides of the box, the gradient is 0, and you don't actually get a net acceleration. So if you're pushing the same from both sides, it doesn't accelerate. You have to have a gradient in the pressure to actually lead to an acceleration. And then this is the external force. Okay. One more trick. We did this before with the temperature budget, and nobody probably noticed. I can distribute this out on those 2 terms, time derivative. And what do I get if I do that? It's a product rule, right? What is that equal to? Two-thirds. Yeah. So we put the row out front and then d by dt and dj. And then the other one, just switching. dj, d by dt, row. This guy. This one is the first one here. Times uj. If you do that on this term as well, it gets complicated because there's a ui one and that one and that one and whatever, but you end up with a term that's uj times this term. What does that mean? I have UJ times I. What can I say about that thing? It's zero because this part is zero. So if that's zero, then I could cancel out half of the 4 terms that come out of this. This is the other half. This is the part that doesn't vanish, which would have the row out front. And look at this carefully. That's the material derivative of the UJ. So the material, this form, the flux form it's called, is the one that has the density inside. There's a flux through the surfaces of momentum flux being carried in. The divergence of the flux is the thing that gives you the rate of change in momentum inside the box. The material derivative is just one conservation of mass away from that. And the quick way to remember is that this one has a row in there. And this so you're basically sticking a row in there and then taking care of mopping up the extras with the conservation of mass. Okay. This one is more convenient to think about in this context because it's obvious what's coming in and out of the box. This one, like, how do you do like, this guy's a divergence rule theorem. What is that weird thing? There's a velocity on the outside and a different one on the inside. Like, how do you do this one is easier to think of for the box. Okay. Any questions on that? We're just starting to get used to momentum equations. So there are a lot of things that are flying. Okay, so let's do the hydrostatic balance. The water is not moving. Okay, so the water is not moving. We take our budget. What happens to this term? It's zero because there's a velocity in it. What happens to this term? It's zero because there are 2 velocities. Okay, those are all gone. So it's just that's 0, and here's the other side. So the other side is equal to 0. So we can solve that equation. The pressure gradient is equal to the forces applied. Okay. What force? Well, maybe let's think about gravity. And the force of gravity per unit volume is minus rho g. And now this is actually in the z direction. It's not a vector anymore. So this is not the bold g. This is the g that is the acceleration. Is just that 9.81 meters per second squared. Okay. We only have one kind of derivative left. Z derivative. That's derivative in the vertical direction. And here we had t derivatives, x derivatives, y derivatives, z derivatives. So what kind of equation is this? And what kind of equation is that? The hint is there are 2 different applied math classes. This one has more than one kind of derivative in it, so it's a partial differential equation. This one has only one kind of derivative in it, so it's an ordinary differential equation. It might be really complicated because nobody told us that rho doesn't also depend on y and time and all kinds of crazy and weird boundary conditions and all kinds of stuff, but there's only one derivative that we're messing with. Okay. Yeah.
You didn't assume an incompressible.
Didn't have
get to the last equation. That was just conservation.
It's in the last one, it was conservation of mass without incompressible. To get this, these 2 are equivalent always without conservation of mass. I mean, without conservation of volume, just conservation of mass. So they're just the same, different ways of writing the same. And so the material derivative is the one that people like to think about because it looks linear. It isn't linear because there's this term, but it looks linear. And so people like to write it looking linear, but it's actually hiding some nonlinearity. This one is obviously nonlinear because it's got a product of things inside of it. So that's something that's different. Okay. But this is the target of our gravity balances the pressure gradient in the direction of gravity. Okay, so what does that mean? How could we're going to start interpreting this, but what is it like? Just how would you solve this equation, or how would you interpret that equation?
Pressure is only a function of that.
Pressure is a function of depth, maybe among other things. This could also be a function of
Right.
time or y or something else. And we don't actually even know if it's not a function of depth as well. So this might not be that easy of an equation to solve. If the density is variable, this could be a very hard ordinary differential equation to solve. But what if the density was constant? Could we solve this equation? We can integrate both sides with respect to z. I get pressure on one side, and I get minus rho g what on the other side. I get minus rho g, whatever the top one is, minus whatever the bottom one is. And these are z levels. So it's telling me that between different z levels, pressure is changing some amount, and that amount depends on gravity and it depends on density. The farther apart I am, the bigger the pressure difference is going to be, okay? And I might choose something really convenient. So what would be convenient? Like, for what, for one of those? 0, like, it might be convenient. Suppose we just ignore the atmospheric pressure, and we take the surface, the pressure would just be atmospheric, so we can call the atmospheric pressure 0 if it's not actually that much. And then this would go from the surface down to whatever depth. So we could say this is the surface minus z. We can put that inside and make this less crazy. Okay, the pressure increases linearly with z when the density is constant. Is that true in the atmosphere? Oh, you have to How does the pressure change in the atmosphere? It goes down as you go up. This also goes down as you go up. If you start at the bottom and go up, it's still getting less. But this one's going linearly. In the atmosphere, it actually goes exponentially. So we're going to see how that works. Okay, so this little slide where it says review of balances, for the next few weeks, we're going to see this slide and its partners over and over and over again until you know which terms in the momentum equation balance, which terms in the momentum equation. The hydrostatic balance is the pressure balancing gravity in the vertical direction. This is just doing exactly what that is, except it also makes the point that this integral of density times g, the z, is just weight. It's mass times g, but it's weight per unit area. So like all the heavy stuff on top of you is how much pressure you got where you are. And if you start up at the top of the atmosphere where there's nothing heavy on top of you in space, and you go down and down and down, that's actually the weight of everything. So the 1 atmosphere of pressure is 1 atmosphere of mass per unit area. Every 10 meters in the ocean, we get another atmosphere of pressure. 1 meter is 1 decibar. An atmosphere is about a bar. So how much does the atmosphere weigh in meters of ocean? 10 meters of the top 10 meters of the ocean weighs the same as the atmosphere above it. The ocean only covers 72% of the Earth. It's a little bit more complicated because then it's like about 72. So it's like 7.2 meters of the ocean weighs the same as the whole atmosphere, including the atmosphere over there. Okay, which is cool. I mean, that's just a weird way to think about it. So the ocean's 4 kilometers deep. So it weighs 400 times as much as the atmosphere. So when we talk about that heat capacity, that it was hard to warm up the ocean, and we said it's because water is special. It's also just because the ocean is really heavy. It weighs a lot, and so it's hard to warm it up. Okay, so here's one way to think of this in terms of density variations. This is another graphical clue you will see over and over again in this class. A short and dense stack, like a short stack of bricks, weighs the same as a tall stack of pillows. Maybe not exactly the scale, but the point here is low density stuff, high density stuff, you can get to the same pressure depending on how much of the stuff there is above you in height. So frequently we are going to think about light water in the ocean next to dense water in the ocean. And the sea surface height is also going to vary from place to place. We may find that the sea surface height is high above light water and low above dense water. And so when you go down to a level at the right level, it'll be the same pressure because the sea surface height variation will be canceled out by the density variation underneath. Okay? Key concept. In fact, that's what happens in the picnic line. The places where the picnic line is depressed deep are the places typically where the sea surface height is high. And vice versa. When the picnic line is close to the surface, the sea surface tends to be low. And that tends to make the pressure below the picnic line more uniform than it is in the picnic line or up near the surface. And we're going to keep doing this a lot. I realized that was a lot. So, but what about just as we're thinking about this vertical structure, like how does the pressure increase? And because the picnic line has light stuff above it and dense stuff below it. So how fast is the pressure accumulating up here? Slower than down here. We don't know how much slower because we don't know, there's no numbers on this, but we know that above the picnic line, the pressure is accumulating slower than it is below the picnic line where the water sets. How about the atmosphere? Okay, here's the potential temperature. Oh no, here's the actual temperature, not the potential temperature of the atmosphere. Oh Lord. Here. And then here's the pressure, and the pressure is labeled in factors of 10. So pressure, I can read off of this. Temperature, I can read off of this. What about density? What's the density doing here? There's this huge temperature variation. There's this huge pressure variation. Like a lot of confusing things to think about. All right. Hydrostatic pressure in the atmosphere. Here's hydrostatic. Works just as well for a liquid and a gas. Here's the ideal gas law. So density times this constant times the temperature is equal to the pressure times the molar mass. This is not always the way that you write this. Sometimes you write PD equals nRT, but this is an equivalent one when volume is shifted around. Okay. So the product of density and temperature is pressure. That's confusing. What if we forget about the temperature variations for the moment and just say, well, it's just all one temperature. Let's just forget about all the, let's pretend that that's just all 220, all the way top to the bottom, isothermal atmosphere. Now, what does it say? It says constant, constant, constant pressure is proportional to density. Let's plug that into here. The pressure dz is equal to something proportional to pressure. Okay, how do I solve that equation? This one was the easiest ordinary differential equation to solve. This is the second easiest ordinary differential equation to solve. What's the answer? Pressure is some initial value at 0. Times what? Minus. Right. If I take the derivative of this side, I pull down a minus c. I And so it equals itself approximately. And there's the thing in the derivative is also on the other side, you're gonna get a most potential. So here we go, that's the external flow. And what does this say about the pressure? Pressure, and then that kind of isothermal atmosphere drops off exponentially. Like this, and if we want to be convenient, we can just think about that coefficient as being a height. And then, you know, like what it really is like this factor and the temperature you chose and all kind of tangled up. But in the real atmosphere, that height's about 8 kilometers. So the pressure drops by a factor of E every 8 kilometers as you go up. So a factor of E is like roughly 3. So at the top of a mountain, a tall mountain, really big mountain actually, the pressure is only a third of what it is at the surface. About an E smaller. We could have done exactly the same thing and done it in factors of 10 instead of factors of E, and we would have found these 10s dropping off. So the pressure is decreasing exponentially. A factor of 10 is 15 or so geometric height units, kilometers, 15. A factor of E in 8 kilometers, E times E, sort of 10, okay, 16 kilometers, 10.
We make the isothermal assumption.
We made it because we did not want a non-linearity in the function for pressure. So we wanted to plug in for density here and have something that made our equation here simple to solve for. I could have written it this way with the height being a function of temperature and then worked very, very hard or done a numerical integration using those real temperatures as I went up to do this. But if I assume it's constant at about 220 Kelvin, it comes out to about 8 kilometers. And so it's just the pressure dz is minus pressure over 8 kilometers. Okay. And it's only to make our lives easy that we did the isothermal atmosphere. It's not really an isothermal atmosphere, but it is pretty real that the pressure decreases exponentially, even though it's not exactly isothermal. Okay. We play exactly the same game. This is where things start to get interesting. It gets interesting because instead of a pressure, instead of a density that's proportional to pressure, for seawater, the density is pretty much constant. We already talked about the fact that in the isothermal atmosphere, in an ocean, the variations of salinity and temperature don't change the density that much, right? And so if they don't change the density that much, they don't change the pressure very far away from the hydrostatic pressure. And so this hydrostatic pressure is a decent approximation of the pressure with depth as we go down. That's that thing I keep bringing up, 1 decibar per meter. This is about a rho naught G is very close to a decibar per meter. That's where that factor is coming. Okay. Which is, and then they worked out another one thing in terms of pascals. Okay. So we said this when we were talking about the temperatures before, but here's our equation of state for density. So density is some background density minus this term. What does this have? What does this say? Temperature versus reference temperature. When the temperature goes up, what happens to density? Goes down. So this coefficient, negative sign. Salinity, when salinity goes up, what happens to density? Goes up. That's that one. Pressure goes up. It compresses a little bit. That's that one. Cool. So how much do you have to heat this to make the density go up by a factor of 2? Well, we need then value of that coefficient, right? We want to make this term equal 1 to change that. 5,000 Kelvin is how much you need to heat it based on the normal value of that parameter. There's not a 5,000 Kelvin variation on the Earth. I don't think it even like molten lava is like 5,000 Kelvin. That's really hot. Okay, that doesn't happen. Salinity You need 13,000 parts per parts per thousand solved. AKA, you need 130% of the thing to be solved, which means that it's more solved than there is mass of solved. So that doesn't make any sense. Like that's also not possible. And I mean, this is a linearized equation of state, so it's a little bit oversimplified, but these two are definitely not happening. And then with gravity, this guy has the interesting property that it's actually equal to 1 over the background density times the speed of sound in whatever fluid it's in. And so the speed of sound in the ocean is about 1,490 meters per second, really fast, faster than it is in the atmosphere. And so what you need is you need the pressure variation, so the G times the depth of the ocean from top to bottom, that's just dz from this equation we were talking about, to be greater than 1,500 meters per second squared, or you need the depth of the ocean to be 200 kilometers deep. So how deep is the ocean? 4 on average. Deepest, 15, not 200. So there's not enough variations in temperature, salinity, and pressure to make this change by a factor of 2. So we're always plus or minus less than 100%. In fact, it's a lot more like 3% plus or minus total. So we can be nearly incompressible. Our density is nearly invariant. Our pressure is nearly hydrostatic. Okay. So is there a consistent way to combine these eyes together? Hydrostatic flow, incompressibility, potential temperature and density, end up with sensible and consistent equations of motion. Yes, there is something called the Boussinesq approximation, which you make all of those approximations all at once. And so your density is the background plus a little bit, which means the pressure is the hydrostatic pressure plus a little bit. That's the relationship between the hydrostatic pressure and the background density. And this funny ratio, which is going to appear a lot, is buoyancy. So the buoyancy is just gravity times the variation in density over the background density. So when the density is a little bit low, you're buoyant, you tend to pop up. And when it's a little bit high, you're dense, you tend to sink down. So you can go through the game and plug into the equations of motion and figure out this, which I don't think I'm going to even go through. But the point is, instead of this version of the equations, you can get this version of the equation where you have something that's playing the role of the pressure, which is called the geopotential, and something that's playing the role of gravity, which is the buoyancy. So when you're buoyant, you tend to accelerate up. When you're less buoyant, you tend to accelerate down. But the buoyancy isn't the total density, it's the density in comparison to the water around you. So the buoyancy is a relative amount of density. Sense to people? So before, when we said this term just needs to be small in comparison to G in order to be hydrostatic, not quite right. It actually needs to be small in comparison to the buoyancy variations. So it's a little bit lower threshold. It's a few percent of free fall is when you start thinking about this guy being important in the balance. And even then, the leading order balance would still be hydrostatic. This would just be the deviations from hydrostatic cause some accelerations. We can play the same game in the mass equation. So our mass equation is this, or the other form we just wrote. If I plug in for density with background plus a variation, what's the derivative of the background density? 0, it's constant. So I can just replace that with the variation. This guy out front, I get the total part, but this thing is small in comparison to rho naught times this thing. So conservation of volume is what we get if we play this Russianesque approximately. So those things that we talked about a little, like when we were talking about the estuaries, we just went to this one and said, don't worry, this is sort of the game. It's because of this part. So the thing that goes together with conservation of volume is hydrostatic pressure being the dominant pressure accumulation. And the last thing that we did, we talked about the buoyancy frequency, where you put something down and it bounce when you're in a stable stratification. This is going through that derivation and solving a slightly more complicated ODE than the one we solved. Actually, it's PDE. So solving for vertical velocity as a response to a deviation from hydrostatic pressure. So if you lift your out of your, where you find yourself in an anomalous buoyancy, you're going to start coming back, and that's where this buoyancy sequence is. All right. Last thing I want to say, how fast is that buoyancy frequency? How stratified are the oceans? Is there background density variation? Yes, there is. We have a picket line. How fast does it bounce? 1 in some crazy units. This is the background. It's up here in the picnic line, it's more stratified, the numbers get bigger, so you bounce faster when you're more stratified, slower when you're less stratified. And these are actually in cycles per hour. So here you're bouncing once per hour. Here you're bouncing once every 2 hours. Here you're bouncing every 15 minutes. That's the kind of bounces that you get in those density variations in the interior of the ocean. And it also varies from place to place. And now this is kind of showing the same thing. Low numbers here away from the equator, high numbers here near the equator. So less stratified, slower restoring times, more stratified, faster restoring times, and so on. You can share those and see what you think. And the last point is just a measure of the surface elevation, sea surface height. This is a map of the currents, the depth integrated currents. Just notice that they're kind of the same shape. So the next thing we need to do with hydrostatic pressure is figure out what it does to horizontal movements. Because the hydrostatic pressure varies from place to place. That's what we're onto, and that balance will be called geostrophy. Yeah.
What kind of like sea surface height differences? Yeah.
About a meter.
Like, no, is that like,
Over 40,000 kilometers, it goes up and down about a meter. So this is, I've actually got a different version of that figure that actually shows it. So this is the pressure variation at 5 meters depth, and it goes from 7 meters equivalent to 3 meters. So it's plus or minus 2 meters. And so people will tell you that they can see the Gulf Stream higher and once it's middle. It's like 100 kilometers, 1 meter, can't see that. You can see the color, it's different color, but it's not the elevation I can see. But we can measure that from space. So easily, like we've been doing that for a couple decades. So part of the game here is that we no longer have to do a lot of the futzing around because we didn't know what the sea surface height was because you can't measure it from the ship. Okay, hydrostatic pressure is this balance. Next time, we're going to talk about other forms of balance and more chance to discuss things. Cool.